welcome back to this second part of this webinar. Originally, Hydroflex had planned for this public web workshop in Sweden during this week, jointly in collaboration with this Swedish Water Power Center, SVC, which we had, of course, to postpone due to COVID. So these series of webinars are the replacement for this. So for this second part of the webinar, we have invited two representatives from industry, Øyvind Lindebo from ABB and Bo Hernus from Voigt, to participate in a kind of a panel discussion, but also have some industry point of views on the development in the project and maybe more generally on the development within this field. But we'll also come back and discuss some of the remaining questions that we have from the keynote speeches, and if you come up with other questions. So then I'll give the word to Øyvind Lindebo from ABB first.
Thank you, Bjarne. Well, first of all, thank you for those two presentations. I must admit that I did not understand every bit of it, but my impression is that we are looking at quite promising solutions for the hydropower plant of tomorrow. I've been asked to comment on the market and development opportunities in an industrial perspective. So my initial comments are therefore more related to the commercial aspects of the converter-driven solutions that have been presented today, and more than the technical ones. First of all, I think it's important to have at least some idea that the solutions and the concepts that we are working on are and are developing are, so to speak, financially viable or will be financially viable in the future energy market. And that is leading to the simple question, are we able to sell the equipment? Will this new way of controlling and operating the generator and turbine contribute to either higher income from energy production, or will it contribute to lower operational cost for the plant owner by means of less maintenance cost, for instance, or by means of prolonged lifetime? And are the investment cost of such variable speed solutions at a level that the power producer is able to achieve profitability? Maybe not today, but in a longer perspective. It's quite clear that being able to adjust the speed of a production unit may contribute to both higher income and lower cost. If you look at the income side, it's obvious that being able to adjust the speed of the production unit will lead to a better operating point for the turbine and thereby higher efficiency. And even if we take the losses of the converter into consideration, and this is specifically the case if we have a pumping generating unit that uses the same runner in turbine and pumping mode, where we can always operate at the best point, both in turbine and pumping mode. Use of converters will also contribute to less wear of the machine. Smooth starting in pumping mode may be the most important feature that will increase the lifetime. And in some situations, you may have less starts and stops since the pumping unit can be operated at part load, and also less wear of the turbine since you can avoid unfortunate operation modes such as cavitations, for instance. So we would expect less maintenance and improved lifetime for the machine, but on the other hand, it was also mentioned today that the converter may cause some additional stresses on certain generator components. And of course, maintenance and lifetime of the converter should also be considered in this picture. There is one advantage with variable speed drives that I suspect is underestimated, at least in relation to payment of services. And That is the increased dynamic behavior of the generating unit with respect to the grid and its contribution to increased grid stability. The first presentation today, Max pointed out about various ancillary services that may be provided from a converter-driven hydropower unit. It will be able to generate or consume reactive power in both modes, and it's also able to inject active power to the grid almost instantly by using the inertia of the unit. So a converter-driven generator is in many ways the perfect dancing partner to less responsive thermal power plants or wind power in a remote area with a weak grid. Some of the services, and it varies from country to country, but some services are commercialized today, but the compensation may be too low compared to the possible savings in grid investments, and hopefully such services will be priced higher in the future. The compensation regime and pricing for ancillary services is a key trigger to profitable investments in converter-driven generating units, since I believe that only improved efficiency and less maintenance cost alone, they will never be sufficient to defend such investments. So are we able to sell it? I would welcome an analysis showing how the investment cost of the converter solutions are balanced with the expected increase in income and reduction in maintenance cost, and also then taking into consideration the expected future compensation regime for grid services. And this profitability analysis should be done for both brownfield, that is existing power stations where you can redesign the generating unit, and also for new hydropower plants. And I think it's important to know where we are today and to get the first indication that we are on the right track, and that we are on a track that is leading to a market-wise sound concept. So my first question was, are we able to sell it? The next question is naturally, how many can we sell? What is the market potential? I think it's also interesting to check and to see how much the grid stability in a large area is affected by a converter-driven hydropower plant. I mean, how many converter-driven units do we need to achieve the required grid stability? This will of course vary from area to area, but such investigation or such study will give an indication of the market potential. Should the 25% of the power plants be converter driven, or will 1 out of 10 plants make the necessary improvement? And Max touched this issue at the end of his presentation. And even in the case with 1 out of 10, I think that the market potential for redesigning existing conventional hydropower plants with converter driven units, that is really a huge market. So to finalize, I would welcome firstly an indication of the short-term and long-term profitability of a converter-driven hydropower plant, and secondly, an indication of the market potential for such power plants. Thank you.
Thank you, Øyvind. I'm sure there is a lot of questions following your points there, but I'll still like Bo Hernes also from Voigt to come with his comments, and then we'll open up for the more general discussion afterwards.
Yes, so I just need to share the screen here. How do I do that? No?
Seems to be working, yes.
But still not the presentation mode. Yeah.
No, there. Yeah. No, we see your notes now.
Oh, how do I do that? Never mind. I can take it in the. No, this was not. See. Oh. Okay, you can see it. Oh,
yeah,
okay.
we can see it. Yes.
Doesn't matter. Yes, from the comments, since we were speaking about this from, I come from the supplier side, so to speak, from Voigt Hydro, where we do manufacture the generators and also the turbines. And just to see some comments, because it's connected, my colleagues in Germany, they are also working in this X-Flex Hydro project. And as one part of the project, we have this double-fed induction machine that is continuously developed also now in this program. So just to show you, not an answer to Øyvind, but these more exotic, should I call exotic machines, because they're not that common, but they do exist in a very, I will say this is a very high power, 390 megawatts. So it's quite a high, substantial amount. And two parts. One is storing energy, which is important also to be flexible in energy from Europe. And here you can store energy in a big dam by the water, and then you can utilize with this generator, then you can utilize different nominal speeds, so to speak, depending on the pumping mode or the generating mode, because you most likely don't have both optimum curves, so to speak, efficiency curves for pumping or generating does not coincide, and then you can, so to speak, utilize this by having a different speeds by this double-fed induction machine. And just because I'm quite interested in as the presentations presented also complete conversion of a whole unit where you have the switching. I just want to show in this case the kind of exotic machines, but still commercially driven. This is what's sold to a customer in Europe, and just to show the differences or challenges. We have the left side, the conventional generator, and to the right side, the double-fed induction machine, and then you see that there are more challenges, I would say, compared to the conventional technology. One is that was spoken already, that there will be switching, and then when you have switching, you will have higher electrical stresses, and this you have to take care about in the insulation systems. Of course, the excitation system for the double-fed induction machine is also more complex. I would say you have to have three lines, so to speak, instead of only one plus and minus side for the rotor. And of course, the stator part, this is the standard is conventional. But just to say, they do exist, these kind of units, and there is an interest also on the market side. I would say in China, we have a big interest with this pump storage, and quite often pump storage comes then with this double-fed induction machine if you want to utilize have the highest efficiency. And then, as I showed just the farthest too in Europe, we are currently working with a very big project in Australia. I would say we are still in the design, again, the double-fed induction machines in this snowy mountain. So there are, to some extent, the market. Have not seen this here in so much in Scandinavia. But we come to another thing that we were speaking about in the presentation, and that is the virtual inertia. And this is, of course, of interest because how I see it, our customers, we work in a mature market, and most often the customers don't want to spend too much money, of course. And if possible, if they can keep the, say the rotor in an old power unit, if you can keep the rotor, you will save a lot of money. And if you can do that, you don't have that high cost, but we have demands nowadays, they have changed also, which means these new demands are forcing the customers maybe to some extent to make new rotors. And this is increased cost for them, of course, and half of the machine, so to speak, compared to a full new machine. And that opens up, I would say, for the virtual inertia. So this part is, I would say, very interesting in the presentations. So these are my comments I just want to give you. Thank you.
Thank you very much. I guess it connects directly to part of the question that was in the chat room, but my understanding is that this double-fed induction generator was developed very much because at the time, or maybe even still for the very large units for more than maybe a few hundred megawatts, the converters are still far too expensive. But
Exactly,
what is the, let's say, the breakout point today? I remember Eivind, you said something a few years ago that 70 megawatt was maybe
somewhere around 100 I've seen.
yeah.
In our internal, some in this,
Mm.
some in this region where you have
Yes,
the
but
breakup.
I think it goes in the right direction. I mean, it becomes cheaper and cheaper.
Yes.
So, but what Bo mentioned is mainly pumping generating plant.
Yes.
So the commercial concept is that you can that you do both generating and motor mode, and you use the variable speed drive also for starting of the unit. So
Yes.
you have, so to speak, more. You combine equipment for several functions.
Exactly. It's a, of course, it comes in the.
Yeah, what we have discussed today is maybe it's more like looking at only the generating mode, where we introduce a converter just to support the grid, and not so much to solve other challenges. So
No, that's correct.
So my point is that in order for this to be profitable, I think the key point and the key trigger for commercialization is the payment of the grid services.
I agree, but just to clarify there, I mean, in principle, because there are some ongoing, both in Europe and elsewhere, research project looking at small reversible pump turbines. So in principle, I mean, if you had a 20 or a 50 megawatt unit, then it could be considered to have a fully converted solution, also a pump in a pump unit, couldn't you, or pump storage unit?
Yes, of course. And that improves the payback of the investment, of course.
So I was thinking, I mean, there is a lot of things happening also in wind power and solar power, of course. How much is, and they're showing these curves almost with exponential improvement on the, let's say, cost ratio. Can we expect that also in high voltage solid state electronics, that we can benefit from that development, so we can see rapid development of these technologies, or what is, how do you see, I guess this is both to the researchers and professors as well as to industry out there, this question. How do you see the development? Can we benefit from that tremendous development, for instance, with other fields of renewable energy?
I'll just say something quickly. I mean, I think one of the things with the converters for wind and solar is that they've been able to benefit from the reduction in the costs of the converters and devices for variable speed industrial drives, and this is kind of because they're around about the right sort of power level. But the consequence of this is in wind, that particularly, they seem to be very keen to stick with low voltage equipment. So even with their sort of 8 or 10 megawatt turbine, they're still using a 690 volts converter. So just from people I've talked to in industry, they're saying it's just a huge step up to get to a medium voltage 3.3 kilovolts converter. So to that extent, I don't know if it's as simple, but I keep seeing research papers from ABB describing their wonderful new high power converters. So possibly that will feed into this sort of region that we're looking at. But I mean, I guess it's going to be initially a lot slower than this the rapid advance that we've seen with wind and solar.
Yes, I'm not really up to date what the last voltage levels are, but of course reaching a higher voltage level is a key point for making this technology more usable for hydropower plants. We to avoid transformers and things like that, and to have a normal design of the generators and motors. So, but I really don't know about what the voltage limit is now. But I had a question to Cheng Yun, the last presenter, about the converter that you presented. What is the voltage level for that one, and what would you expect?
Well, if it's MMC or modular multi-level converter setup, then the voltage can goes probably above 3.3 kilowatts. Yeah, but well, it also depends on the switches which we choose for constructing the converter. So if we choose silicon carbide or gallium nitride switches for the converter, then the voltage level can be also higher, I would say.
Yep.
I guess yeah, so go ahead, please.
We'd like to reach 10, 15 kV.
Oh, probably not. Yes. I mean, the medium voltage, the definition of the medium voltage probably it's less than 13.3 kilowatts. So, yeah.
Yep.
Yeah. Yeah, but I mean, the MMC setup, it has been widely used in the HVDC transformation, right? And there, the voltage is it's 100 kilowatts. It's quite high voltage, right? So probably, I mean, there is this kind of possibility that we can increase the voltage level in our converter if we use a MMC setup.
Let's say, I guess this first question goes then to the academics out there. How do you feel that the collaboration is between industry and academic work on this development here? Is there a good collaboration, or is there mainly each working on each side on this? Or can you comment on, not generally, not only for HydroFlex, but more in general, if there, yeah.
Maybe Urban is the best to answer, but I can start a little bit. I think that we are still a little bit in the start of getting collaboration. So far, from my side, it has been a little bit limited in this project. Where we have worked much longer, for instance, in Göteborg, we have the Volvo companies. I mean, then there is much more discussions about things, but hopefully we could get in a better dialogue with industry. But maybe I think Urban, you have much better contacts. What do you say?
Yeah. Well, I can say two things. I sincerely see that this is the hydropower industry is very open about the problems that they have, both from the owner side, but also from the supplier side. So I see that there is a general pool of ideas which can be shuffled around, and people are willing to discuss and share competences, knowledges, and also drawbacks that they see. But then I also see that the suppliers, they are quite hardly pressed economically. So their organization is much slimmer. So it's not so easy to collaborate on developing things per se. but they share information, or are quite open with issues that they have.
I think also one important player here for us is ABB, and I think there has also been some efforts in reorganizing. So maybe now that they have reorganized, maybe it will be easier.
Yeah, and I guess just to comment to what Eivind was saying, that for commercial developers to be interested in buying the technology, there must be a market for selling these services. I mean, at the moment, at least in Norway, I mean, there is quite a significant development of small hydros or units below 10 megawatts, which would be excellent for testing some of these technologies, but they are also very marginal commercially, and as long as there is no market for providing these kind of more exotic services, they won't invest in they will buy the traditional generator as cheaply as they can get them, and not invest in this kind of more sophisticated technology.
Maybe I can make a comment there. We quite often see that the owner side, they are saying, well, there's no market for these solutions, but you can also turn it around and say, well, if you show the solution, maybe you can push that there will be market, because if they see the benefit from having components like this, they can see the advantage that they can give. Maybe they will actually develop the business also for it. They develop the business model for it. So I think the demonstrations that are available and the openness should be there. It's actually quite vital that we have EU funding and funding from other places to develop technology and actually demonstrate it, because it's only then that we can tell the TSOs this is what we can accomplish with hydropower, and sort of show the bigger gains that can be obtained.
Yeah, no, I fully agree, and it's getting that, sorting out that solution, getting the dialogue with the TSOs, and getting those demonstration units up and running, which is clearly a key challenge here that we have to continue to work on.
I think I thought with the market for this frequency support services, I guess the issue at the moment is that the grids at the moment or the energy mix is able to provide these, there are a lot of players who can provide these services. So as such, there's not a particular sort of price premium on them. So it's at the moment, then there isn't or there isn't enough sort of financial returns for such a system. But you can imagine, as say old nuclear power stations and old coal power stations are shut down and decommissioned, and replaced by a lot more wind and solar, then you could suddenly find yourself with a much less stable grid, and grid operators willing to pay a premium for support services. But yeah, then you need to be able to have the system that you can then roll out to provide them.
I think this is true. I mean, in Sweden, we saw or in the Nordic countries, we saw the event of a new frequency control service, fast frequency response. Everyone's been talking about, oh, it's needed, but all of a sudden there was an acute demand for it, and then they came up with another product which doesn't solve all the issues that they want to solve with it. So I think both academics and also the owners, they have a task to show it, to have a dialogue with the transmission system operator to show what can be done, and indicate, okay, this, everyone knows there will be issues, but what are the solutions? Instead of the transmission system operator, they come up with a band-aid solution instead of tackling the real problem.
Yeah, and it's a bit late to start to develop those demonstration projects when you have the acute problem. So I mean, it's at this stage when actually the problem is not acute, and that we can have the time to test out solution that we could actually do this kind of pilots. So I think it's a challenge for us to continue to communicate that and try to see if we can get project or funding or start up some of these demonstration projects.
We have two people from, I see one from Vattenfall and one from Fortum. It would be nice to hear, if you're still online, hear your comments about future market for variable speed and what do you see and how can you benefit from it now, but also do you think that you can sort of push the TSO so that there will be a market? I think about Hans and Fredrik.
Well, I can perhaps comment. Hans Bjerg, do you hear me?
Yes.
Hans Bjerg from Fortum. Well, I think it's a bit premature to give you a clear answer to that. It will evolve as we go, I would say. We are very much interested if there is a market, of course, to supply it. And I have though another thought, and picking the low-hanging fruit somehow. I've had for quite a long time, we had thoughts about how to perhaps better utilize power plants where we have quite a big change in amplitude from the hydro reservoir, larger reservoirs, combined with, in the first case, France's turbines, where we could actually both increase the energy production quite considerably if we had variable speed on the units, and then also reduce the vibrations as especially at lower heads. We have quite sincere vibration risks in those turbines. And if we could perhaps finance it with the increased energy production from those units and combine that with those new ancillary services, I would say that basically the investment would pay itself, I guess. So a starting point would be perhaps to try to identify some kind of plant where you have this situation where you have a big change in the head and you have France's turbines, and then perhaps start not with the biggest ones, but some half-size, semi-sized units up to 50 megawatt or something. I think that would be quite an interesting starting point, where you have a double win, not just the ancillary services, but also actually a quite considerable increase of the energy produced. I don't know if that's what you asked for, Urban.
No, but it was a comment about where you see a potential for some of the technologies that are being developed in this project. So appreciate that answer.
Yeah, well, I would say that so far, to my knowledge, it has been a bit too expensive to install such variable speed solutions for those plants. But if we can come down in the investment cost and so on, I think it could be of great interest. It's all about money.
Hello, is Fredrik, are you on or? No, maybe not. I guess another opportunity for, or do you want to ask a question, Arne?
Yeah, or maybe a comment then. Let's see, the first time I was involved in this type of evaluations was in 98 or 99 in ABB. And then we studied the possibility of installing a double-fed machine then in southwest part of Norway to increase the transmission capacity from western to eastern Norway. I think we concluded that we could increase it by 700 megawatts or something due to the increased grid support. But the market is not there. Let's say Sira-Kvina in this case need to buy the machine and Statnett take all the advantages. So you need some market mechanisms for this, and maybe the market or system problems need to be larger than today before really facilitating this. But we have just sent a new application where both Statnett and Statkraft are together with Skagerrak is supporting the project to see, and that is not on variable speed so much, but it's on reactive power. How you could use the generators then to optimize the reactive power flow to take down the losses in the system. So there are some contact points.
I was also thinking about your comment, Max, regarding your question, or you commented that you could in principle also reduce the cost of the generator, or reducing the inertia of the generator, and compensate by using this virtual inertia. I'm not sure, I guess you haven't had time to think or to work on it at least, but I'm not sure if in principle also could even get rid of the surge tank, so that you could, even if you technically have an unstable system, that with when you have all these controllers, that you can use those to stabilize the system just numerically, and then also save cost by cutting down on the construction of the surge tank.
Yeah, potentially. I unfortunately don't know enough about hydro systems. It would be an interesting thing to look at, to like maybe get some sort of topologies in that respect, to sort of to see how you could do, because obviously, yeah, you could probably vary the power a lot more quickly, or vary the vary things a lot more quickly than you could do through the guide trains. But I think that's one of these ones where a fancy controller like a model predictive controller could be very useful. I mean, you've got a fairly slow operating system, so working out a long way into the future each time step should be like fairly straightforward. So yeah, it's interesting to look at.
Just a comment on that, Bo Hannes here from Voigt. I would say that if you're considering the inertia of, so to speak, a generator, there are other restrictions from the turbine side, and it's not trivial just to, so to speak, decrease the inertia of the generator, because it will end up, so to speak, to one part, it will end up with a certain inertia because of the dimensioning of the unit. I mean, you have to have it for mechanical reasons. So I would say normally when we are in design, then we calculate the unit, and then we end up with, so to speak, one inertia, and then maybe if the customer has demand or the turbine has demand, depending on how to handle the turbine, then we might increase it slightly or decrease it slightly, whatever. But I would say it's not the big. I wouldn't say there's a big gain in that from design perspective of the units.
So this idea just came from a paper that I had read. I can't remember the authors off the top of my head, but what they were looking at the optimization of a synchronous generator that was going to be connected to a converter connected hydropower system. Yeah. And so they were looking at things like, could you change the operating frequency, or could you reduce the amount of material based on the fact that you don't have to provide any reactive power from the generator? It was things like that to say if they could get a cost reduction. But one of the things that they did was they kept the generator inertia the same. So I would
No, of course I mean it's always individual, depends on one unit station to another, so it's not a fundamental thing. But I would say quite often in the branch they are speaking about the natural inertia, but this in principle depends on the design principles you have for your generator, so to speak, and you will end up with something just from caused by the design to handle poles and so yeah, sure.
But for the smaller units, you often have a flywheel in order to reach the.
Yeah, that's correct.
So for smaller units, you may drop the flywheel.
Yes, that's true. That's true. It's an extra we have to put on. Yes.
But another question was for this. I mean, for this power grid. Is there a possibility that we can avoid investment in a new power line or a new transmission line by introducing a converter-driven power plant? And so we can save the investment cost and show that to Statnett, for instance.
So I'm not sure. That would, I guess, that would be more related to the ability to store and release power in order to to balance the power flows temporarily better. And I guess that's a factor of the variable speed. It's not so. I didn't mention at all the ability to vary the pumping power, and that seems to be like quite a key thing with the variable frequency use of hydropower. And yeah, that could allow better optimization of the transmission infrastructure.
Yeah. Yeah, I think you're right. But also, I think, but then it seems like Arne, I think that was part of the this project, that the proposal that you're working on is looking at how you can optimize, but then looking at several units in the grid, how you can optimize transmission capacity and thus avoid grid development projects and save the cost, isn't it?
Yeah. The idea then was to increase the capacity without, let's say, install other equipment in the power grid, because the transmission capacity is normally limited by stability and not thermal or water stroke. So it's the stability that very often limits the transmission capacity.
But just a question, Bo. I mean, if we started now with developing, let's say, a small unit where we are liberating ourselves completely from running at the synchronous speed, would there be benefits or let's say gains to in the generator design, that you could, if we are not restricting ourselves to a certain inertia, not to a certain speed, could we save a bit on the generator design?
Yeah, I think to some extent you can, but as always, you have to look into the details.
Yeah.
I know by experience. But as Urban showed about how to say, non-laminated or without damper bars. Of course, I mean, what I showed about the more exotic machines is that, yes, I call them exotic because they are more complicated, more challenges. If you can make the rotating part simpler, for sure you will gain money, because this is a cost driver. You have more challenges in handling the components, and if you have fewer components, it will be cheaper, so to speak. It will make it easier life for the designers to make this, because this is what we have to struggle with always, with the rotating parts. I would say the static part is normally not an issue itself. It's the rotating parts that's the biggest challenge in hydro generators, I would say. So if you can make that, as Urban was looking into, then make it less complex, then you will for sure save money. But I would not expect too much. We have done many times cost, so to speak, internal cost cut projects, and nature is nature.
Yeah.
Maybe you can save some 5%. I don't know, but normally not any big amounts. mainly because it's, I would also say it's a mature market. It's a mature product in many ways. So I wouldn't expect big gains, but
no,
always something.
I'm not sure if, I mean, I guess part of the reason why there's been such a cost reduction in wind is that you are able to standardize and have huge volumes or large series. I'm not sure if we are not liberating ourselves from synchronous speed, if we are able to somehow develop some more standard designs.
Yes, this would be, if you for sure, that would take down the cost, because in principle nowadays, I mean, when we do generators, it's more or less unique for every project. They are, and of course this is a cost. You have to redo the design, and say if the design takes somewhere between somewhere around 8,000 to 10,000 hours to doing the design. If you do it a second time or third time or fourth time and you don't have this, I mean, if 10,000 hours is 10,000 times 1,000 kronor, then you will have a lot of money that you will gain. For sure. Here you will have some, of course, and then also you can do it in series, in mass production. It will go down in price for sure. So there is a big gain if you are unrestricted, because this is also exactly, I was heavily involved 10 years ago in a small hydro project we have internally in Voigt. We have done a small hydro design for smaller units up to 40 megawatts, and those were also the intention to have steps, so to speak, so you don't have to redo the design every time, because the design becomes a big cost in the projects, especially in the small units. If I say 1 megawatt unit, 10,000 hours, this is a tremendous amount of money for 1 megawatt unit. They cannot bear this cost in the long run. So yes, there you will have a big gain. Yes, you're right.
Igor, I'm not sure if you're still on, but if you are, I mean, is there something similar? I know in your PhD you're mainly focused on optimizing performance, but is there a similar opportunity that we could standardize more, let's say, units if we are more not governed by the synchronous speed?
Not sure if I understood your question fully, Arne.
No, my let's say input point was that within wind, for instance, you see these curves where the costs have dropped dramatically the last 10 years. And I think a large reason for this is that they have very huge volume, so they get a benefit of the scale. So if we could find a way to have more scalable hydropower, so we could produce more similar units, maybe could have a more cost benefit also, and then be more competitive for hydro in the future. So if this use of converter could have like a technology where you are more standardizing the designs, if that could be an opportunity.
Yeah, well, regarding the design, I don't think that the converter or the variable speed capability will help to standardize hydropower turbines. They still remain highly, how do I say it, highly customizable or custom design, custom solution. So yeah, I don't think that we can produce standardized units, at least for maybe for smaller hydropower plants, for smaller power output, we might think of something, but for the larger units, it's definitely tailor-made. Hope that answers the question.
Yeah. No, that's good. No, I think, I mean, anyway, I think if we have to start with some of, so I mean, that's something probably that would be interesting to look a little bit more into detail, let's say for units up to 10 megawatt, if you can, because anyway, from this technology, it's really hard to defend building a 200 megawatt fully converted solution at the moment, but maybe a 10 megawatt one could be, you could have these as a kind of demonstration projects. That's probably an interesting avenue to look more into.
Yeah, I totally agree.
Maybe I can make a comment about just the boundaries of this, the whole project. The call from the European Union was about increasing flexibility in in terms of up to 30 starts and stops per day and increased ramping rates. So all this, some of the aspects that we discussed today, they lie on top of this underlying boundary condition that we have from the European Union. The request from them to develop units which can tolerate this amount of starts and stops and high ramping rates.
Yeah, no, I think, and I mean, this is, I don't recall exactly what in the call, but I mean, this is meant to be development of new technology. So I mean, I think it is very interesting, and we've seen during the project that by challenging ourselves, we are seeing that we are coming up with new interesting concepts and possibilities for future development. And clearly, maybe the Nordic system is not the best representative where these challenges will be the biggest. I've been involved in commissioning of a unit or in a power plant in Liberia where the whole national grid was run on one unit with large stability problems. So there you could have some of these. It would be excellent to have some more sophisticated control algorithms to make sure that we could stabilize things. And maybe then also there is a lot of development with microgrid also, and using maybe small hydro plants with microgrid solutions and then using fully converted could be interesting opportunities, because if you have a low head turbine, it's not so easy to have a micro with the Francis turbine, which cannot operate at very low load. So then maybe this is opening opportunities also for development elsewhere. So if there is, I don't see any more questions. Yeah, go ahead.
Sorry. Actually, I was just adding to your comments. Once I was in one of the power plant in India for the efficiency measurements, and then there was around 3 or 4 hours measurement time, and in 4 hours there was 3 times total load rejection of the unit. So instability in those countries are very high. But I also want to ask, kind of discuss, if we consider 30 starts and stops, have we thought what will be the consequences on the shaft which is connected between the turbine and the generator? Stresses on the shaft as well during startup and shutdown.
Yeah, well,
no,
I can just a quick comment. I was, from design perspective, I would say what we have faced, I would say normally the shaft is not a problem, not an issue. It's other components. I'm a mainly generator guy, so I'm a generator guy. But in generator, yes, there are some complicating factors with a lot of start and stop due to the, in this case, it's more due to the thermal, related to thermal. If it goes completely cold and completely warm, and this part could have effect on fatigue and so on. Of course, if you do a very fast ramping up, that can also be that you're passing by and vibrations, and this part that can also have some negative factors for the unit, of course. But I would not expect the shaft, normally not the shaft itself. But I guess that from the turbine side, they also have some issues with if it ramp it up too fast, so to speak.
Yeah, but of course
it has to be considered.
Yeah, I agree. It has to be considered, but and it must be taken into the design. But it's not considered to be maybe the most critical. But I mean, in the Nordic, it's an extremely high number. But we have seen before from for instance, the Norwegian period have the pump storage plants in the UK. They have 10 what they call mode changes during the day. Or during 24 hours, so that includes going from pumping to turbining and starting and stopping again. So I mean, and I think this COPS2 in Austria is even more extreme in the number of mode changes it's going through in periods. So it's the order of magnitude in some of these settings, I think is will or may be needed in the future in some regions.
The shaft diameter probably will have a larger impact. If the diameter is smaller and then have a very high number of start and stop, then the stress and the strain in the shaft could be very high.
So I just noticed there was a comment down in the chat about battery systems, and I think that could be then an important thing in the future. I mean, we mentioned about economies of scale and things like that. In the battery system, you're probably using low voltage converters, which are fairly well understood, and there'll be a huge benefit on the battery supply from electric vehicles, just kind of in general increasing the supply of batteries. And that's before you get into ideas like vehicle to grid and things like that. So I do feel that batteries are going to be important in the future, or they are going to benefit from economies of scale, and that is something that you would have with a variable frequency hydro system would be competing with. So probably the ability to provide ancillary services, frequency support, is not going to be the main driver of an uptake, but could be a useful addition.
Yeah, no, I think you're right. So I mean, that's why it's so. If you are a supplier and if you are a power company, I guess it's interesting times, but maybe complicated times, because you don't know exactly where the market is going, and if you're doing investment or planning for 30 years ahead, then or 40 years ahead, then it's not so easy to know what kind of solutions you're going to select.
Arne?
Yes, Arne,
yeah, I can comment here. Yes, it's kind of hard to, technologies are expensive to develop, and it's hard to predict where the market is heading. So we cannot just develop all the technologies today and just hope that one will work in future. And with variable speed, at least, there are other aspects that we did not address in Hydroflex, other important aspects, such as the structural integrity of the entire power plant. Of course, when you start to deviate the rotational speed, we'll have changes in the torque, and increases in torque when reducing the rotational speed. And also the performance of the truss bearing will be problematic once we start changing the rotational speed as well. So as Chirag has commented, there will be maybe the shaft will also experience some problems. Well, there are many other aspects that we did not address in Hydroflex, but hopefully in future we will get back to those aspects as well. That was my comment.
Thanks, Igor. I think maybe then that's a good closing point, that there is still more work to do. So I will thank you very much, keynote speakers, and also participants from industry coming with interesting comments from their point of view. We have been